Okay, students, here we go. Yesterday when I met with the whole class online, the recording feature it malfunctioned, so I was unable to record what we spoke about. So I'm redoing this topic, these two complicated topics, and then I'll post them on Canvas. So topic number one that I went over yesterday is under the category on your notes of 3 factors influencing external respiration: thickness or thinness of respiratory membranes, partial pressure gradients of gas, and gas solubilities is number 2, and number 3 is the ventilation perfusion coupling. So the ventilation perfusion coupling, it can be confusing. It's not greatly explained in the textbook, in my opinion, so I'll do my best to simplify it for you. So we're talking about 3 factors that influence external respiration. That means what happens in the lungs. We inhale air, gases are exchanged with the pulmonary capillaries so we can get oxygen into the blood and CO2 out of the blood. That's external respiration, what's occurring at the lungs right here. So number 3, the ventilation perfusion coupling means this. The word ventilation just means the movement of air, so breathing. Think of ventilation as breathing, in and out, in and out. Perfusion means blood flow, so it means the movement of blood through blood vessels, in this case the pulmonary capillaries. So that's step 1. Step 2 is to understand what regulates or dictates ventilation and perfusion. So the biggest factor that controls ventilation, which is breathing, a movement of air in and out, are levels of carbon dioxide, CO2, in the bloodstream. So there are sensors in our major blood vessels, chemoreceptors, that sense the content of carbon dioxide in the bloodstream. It's levels of carbon dioxide that regulate our breathing, our ventilation. So the higher CO2 levels get in our bloodstream, as they go up, we breathe more. It causes us to ventilate more. That's what actually causes us to take our first breath when we're born, is rising levels of CO2 in our bloodstream causes us to take our first breath. Likewise, when you're exercising, what causes you to breathe heavier more quickly is actually levels of CO2 building up in your blood from your working muscles. All right, so CO2 dictates ventilation, and levels of oxygen regulate or dictate perfusion, which is blood flow. And how that works is same thing. Chemoreceptors in our major vessels monitor oxygen levels in the bloodstream. So the higher the oxygen, what they do is they sense where oxygen is best able to be grabbed in the lungs. So what happens is arterial diameter changes based on oxygen levels. Arterial diameter changes to different areas of the lungs where alveolar oxygen diffusion is best. So it sends blood to different areas of the lungs based on where it can get more oxygen. All right, so just to rehash that, 3 stages or 3 steps or things that influence external respiration, 3 factors are the thickness of the respiratory membrane, partial pressure gradients and gas solubilities, and the ventilation perfusion coupling, which I just explained. Now, the second major topic that we talked about yesterday is the transport of carbon dioxide in the body, in the bloodstream. So I'm going to do that last. We'll end with this, but it's a big complicated topic, so I'm going to use the blackboard behind me to explain this. So our cells, our tissues and our cells produce carbon dioxide as an exhaust, as a byproduct of cellular metabolism. We need to get rid of CO2 because it can become poisonous to our bloodstream, to our bodies, if it stays in our blood. So we need to get rid of it. When we exhale, we get rid of it. Well, how do we get that carbon dioxide from our cells, our tissues, all the way back to the lungs? That's this topic, the transport of CO2 in the bloodstream. There's 3 ways that carbon dioxide can be transported in the blood. The first one is just dissolved in the plasma. So CO2 has the ability just to be dissolved in plasma and travel in the blood. But only about 10% of carbon dioxide that's transported actually uses that mechanism, dissolved in plasma. It's about 10% of all CO2 in the blood is dissolved in the plasma. The second mechanism or way that CO2 can be transported in the blood is bound to hemoglobin. Okay, so I'm going to quickly draw a hemoglobin molecule. This is going all the way back to when we studied the blood. There are 4 iron molecules, and then what we say are globin chains, they're amino acid chains, attached to these 4 iron molecules, 2 alpha and 2 beta. Oxygen, you probably remember, binds to this iron molecule right here. So we can get 4 oxygens on this one hemoglobin molecule. So oxygen binds to iron. CO2 binds to amino acids, an amino acid link out here on the chain. So CO2 can bind to this whole molecule, but in a different place, a different spot than oxygen. So this binding of CO2 to the hemoglobin molecule is not in direct competition with oxygen binding to hemoglobin, which is a good thing. However, CO2 does bind here to this hemoglobin molecule when there is no oxygen bound to hemoglobin, or it binds more easily. So if this hemoglobin molecule has no oxygen bound to it at all, this CO2 molecule will bind here much more easily, much more readily. When this CO2 molecule binds here, we call this whole molecule now carbaminohemoglobin. Just means carbon dioxide is bound to hemoglobin at the amino acid chain. That's the second way that CO2 can travel or be transported in the bloodstream, is bound to hemoglobin. And about roughly 20% of all CO2 in the blood uses this mechanism or transport method. Now the third way is the most complicated. The third way that CO2 can be transported in the blood, and this, by the way, is the mechanism that the majority of CO2 uses, is within a it happens within a red blood cell, but it ends up being outside of the red blood cell. So this circle I've drawn just is a red blood cell, an erythrocyte. Now this erythrocyte has hemoglobin in it. When it's in the lungs, it picks up oxygen, then it travels to our cells, to our tissues. It releases the oxygen from the hemoglobin. And our cells out here, if that's a cell in the tissue, it uses the oxygen that the hemoglobin let go of, and then the cell gives off carbon dioxide when it metabolizes, when it goes through metabolism, when it does what it needs to do. It gives off CO2. Actually, it's cellular respiration. It gives off carbon dioxide as one of its byproducts. What happens to that carbon dioxide is what this topic is about. So the CO2 has the ability to diffuse into the red blood cell, and then it combines with water inside of the red blood cell to form a weak acid called carbonic acid. So this is just a very simple chemical reaction that occurs, and CO2 plus H2O bound together creates H2CO3, which is carbonic acid. So all we did was combine these two molecules together. We come up with this. Now this reaction can occur out here in the blood plasma. It doesn't have to occur inside of a red blood cell. And it actually does occur out here in the plasma, but it's such a slow rate that it's not significant. It happens inside of a red blood cell about 5 to 50 times faster because of an enzyme that's present only in the red blood cell. And that enzyme is called carbonic anhydrase. Carbonic anhydrase speeds up this reaction, the formation of carbonic acid. Now this acid is a very weak acid and it dissociates, it breaks apart very easily, especially under alkaline or basic conditions. And when it falls apart, when it dissociates into two molecules that are different from these two. It dissociates into hydrogen ions, which we call protons, and bicarbonate ions. So this is a proton, a hydrogen ion, and this is called a bicarbonate ion. That's where the CO2 is now. All we're doing is hiding the CO2, really. It comes into the cell, combines with water to form this acid. The CO2 is hidden here. This acid dissociates into hydrogen ions and bicarbonate ions. Now the CO2 is hidden in here, and this bicarbonate ion then diffuses out of the cell and then it travels back to the lungs in this form, in the plasma, back to the lungs. When it gets to the lungs, I want you to know all this business. When it gets to the lungs, basically all of this happens in reverse. We produce this CO2 and we exhale from our lungs. When this bicarbonate ion diffuses out of the red blood cell in order to travel back to the lungs, at the same time, the cell exchanges this chloride ion with this bicarbonate ion. This process is just equalizing the electric charge. So we trade this negative for this negative. This process is called the chloride shift. It just means we're trading the bicarbonate ion for the chloride ion. I'm going to go through this again very quickly from the beginning. It's important that you know this, understand this. I'm going to expect you to know it for the test. Our cells produce CO2 as a byproduct, an exhaust. The CO2 diffuses into a red blood cell, combines with water. This enzyme, carbonic anhydrase, speeds up the reaction of forming carbonic acid, just combining these two molecules. So we get carbonic acid, it's weak, it falls apart, and it falls apart into a hydrogen proton and bicarbonate ion. This bicarbonate ion diffuses out of the cell. At the same time, chloride diffuses in. That's called the chloride shift. Now our CO2 hidden in this bicarbonate ion travels in the plasma back to the lungs. When it gets to the lungs, it does all of this in reverse, and CO2 is expired or expelled from the lungs. That's the gist of number 3 on this list of how CO2 travels in the blood. It's called as bicarbonate ions in the plasma. Now you know what that means. There they are. There's the bicarbonate ions in the plasma. The last thing I want to say about this is this acid bicarbonate ion business can act as a buffer in the blood, a pH buffer. The definition of a buffer really is anything that resists a change in pH. Dramatic changes in pH are not good for the human body. We need to keep a very, very stable pH right around 7.0. The blood tends to be slightly alkaline, but not by very much. When things in the body, particularly in the blood, get to be too acidic, that means there's too many hydrogen ions present. And this acid can dissociate, and hydrogen ions can then bind to bicarbonate ions to neutralize that acidity. Likewise, if conditions get too alkaline, if there's too many bicarbonate ions in the blood, then this reaction can form and reverse bicarbonate ions combined with hydrogen ions to produce carbonic acid. So this acid, this weak acid, really acts as a buffer. It can go either way to buffer pH changes or shifts from alkaline to acidic, and it helps keep the blood neutral. Okay, that should do it. If you have any questions, I will be available via email. This is Thursday afternoon. I'll try to post this right away so that people who were not at the meeting yesterday can have a chance to view what we talked about. And then tomorrow I'm going to set up a meeting, so look for a post, an announcement on Canvas about a meeting tomorrow.